Hi everybody, this is example or problem number 11 in our chapter 4 review on vectors. And if it kind of sounds funny, I apologize. If the audio is kind of weird, I'm sort of in a smallish room, more like a closet. But anyway, hopefully you can hear me okay. All right, so number 11. It says you walk 375 meters due north and then 525 meters in a direction 35 degrees north of west. All right, well, let's do the due north direction first. So this is this right here. That is 375 meters due north. You might say at north, right? Or you might say 90 degrees north. Okay, it's straight up. And by the way, oops, I got the wrong thing here. This is going to be our origin right there. Okay, and then we walk 525 meters in direction 35 degrees north of west. All right, so it's going to look like that. Remember, we add vectors tip to tail, so that's probably not to scale. That's 525 meters at, this is our right there, 35 degrees north of west. Okay, and the whole trip takes 150 seconds, so that is our time. That's our time. T equals 150 seconds. I thought about making it 2.5 minutes, but I thought I'd make it into seconds for you so you didn't have to convert. Okay, your displacement for your walk, that's what A is asking us for right there. Delta R equals what? And again, you might be thinking, well, why? What's the deal with the R right there? Well, it's not in the X direction, it's not in the Y direction. It just means some other direction other than X or Y. So this is going to be what we call the R direction, whatever direction that is from the horizontal. Okay, I should probably make that a dotted line. So I'm just going to call it R. All right, so that's what we're solving for right there. So we're solving for that total displacement, delta R. All right, well, to do that, we need to add together our vectors, the blue vectors and the red vector. And I probably should have given them a name, shouldn't I have? I'll make the first one vector A, all right? And the second one, or the blue one, or the red one, I mean, I'm going to call that vector B, all right, just so we can tell them apart. All right, well, how do we add vectors together? Well, we have magnitude and direction, magnitude and direction. We need to add them together using the component method. We can't use unit vectors because we don't have the individual components quite just yet. But we're going to add these together using the component method, putting together our table, our vector table. So vector, the magnitude of that vector, the direction of the vector, the x component, and the y component. All right, let's draw our lines down right there. We're going to add the first vector, vector A. I'm going to add that to vector B, oops, which is red, and hopefully get the resultant vector. We're going to call it, we'll just call it delta R. All right, because it's both of A and B are they're displacement vectors. I keep getting the wrong color. I'm sorry. Okay, and this is our total displacement for the whole trip, so it's the sum. Vector R is the sum of A plus B added up. So from here to here, what is that? We're going to find that out, okay? So vector A's magnitude, what is it? That's 375, right? 375 meters. At what direction? That's at 90 degrees north, right? Or 90 degrees north of east, straight up. Okay, how about the B vector, vector B? That is 525 meters. At what direction? That is 35 degrees north of west. All right, so look at it for a second. Why do we draw those little arrows right here? That tells us it's going to have a negative x value, but a positive y value. All right, so the x is going to be negative, the y is going to be positive. All right, well, how do we get our x and y components? And sometimes I write this, sometimes I don't, but it's a little reminder. X is always magnitude times a cosine of theta. Y is always magnitude times a sine of theta. All right, as long as our values are based off of the horizontal, which they should be. All right. So 375 times a cosine of 90. If you know anything about the cosine of 90, anything times the cosine of 90 is going to be 0. 375 cosine 90 degrees, because the cosine of 90 is 0. So that's going to have 0 x component. And if you look at that vector right here, it's all in the y. There is no x component at all. It's not leaning one way or the other towards the x. It's straight up in the y. All right, what is the y value of it? Well, that's going to be 375 times the sine of 90 degrees. 375 sine 90 degrees is going to be 375 because 375. Because the sine of 90 is 1. Okay? And again, this vector is entirely in the y direction. All right, how about the x and y components for vector b? Well, the x component is going to be the magnitude times the cosine of theta. 525 cosine of 35. 525 cosine of 35. That was 34. 35. 430. This is going to be red. 430 meters. But look at that for a second. Is that going to be positive or negative? We said a few minutes ago it's going to be a negative x, right? It's leaning in the negative x direction. So it's going to be a negative x right there. But what about the y? The y is going to be positive, right? Because it's pointing kind of in the positive y direction. So how do we get the y? That's 525 times the sine of theta. 525 sine 35 degrees. I get 301. 301. I'll just round it to 301 meters. Okay? All right. So why do we get the x and y components? Because we can add the x's, we can add the y's. Otherwise, we can't add them unless they're all in like terms. This is all on the x-axis, that's all on the y-axis right there. Well, the x is going to be easy to add because it's negative 430 plus 0, so that's negative 430 meters. What's 375 plus 301? That should be 676 meters. Did I do that right? Yep. Okay. So we're saying our r, you might say our r vector has negative 430 x hat, or in the x direction, and it's got a positive, so that's kind of our delta rx, and it's our delta ry is going to be a positive 676 meters. That's what that's saying right there. So we have the x and y components of vector r. Let's just find what vector r is. All right, what's the magnitude? What's the full magnitude of vector r? If you have the x and y components, the magnitude of vector delta r is going to be square root of 430 squared plus 676 squared. All right, that's the Pythagorean theorem. 430 squared plus 676 squared, and take the square root of that, equals 801 meters. That's going to be this whole length of this vector right here. That's 800 meters. All right, what is the direction? This theta right here, this theta for delta r. For the theta of delta r, that's going to be the inverse tangent of the y over the x values. That's 676 divided by 430. All right. Now I didn't put the minus in there or in here because, of course, if you square a minus, it goes away. Here, you can just use the absolute values. It doesn't matter. We're just trying to get what that angle is. We can figure out what quadrant it's at later. Okay. So what's the inverse tangent of 676 divided by 430? I get 57.5 degrees. Now, what quadrant is that in? The negative x with positive y, right? Negative x, positive y. So that's going to be north of west. North of west. And that is our answer in magnitude direction form. 800 meters, that's our displacement that the person is walking. Starting here and ending up here, they displace themselves 801 meters at 57.5 degrees north of west. They do it in two separate segments, but totally from beginning to end, it's 800 meters at 575 north of west. That is part A. I believe that's part A. Yep. All right. You know what? I'm sorry, we didn't even have to do that. We didn't have to do magnitude and direction. I mean, it's helpful that we did that. Okay. Well, oh, you know what? I'm sorry. Yeah, that's part B. Part B was magnitude and direction. So you're being displaced from here to here, 801 meters at 57.5 degrees north of west. What was part A? Part A was what is your answer in unit vector notation? Well, delta r, we have the answer right in front of us. Something, something, x hat, and, oops, I should probably make this a little bit bigger. X hat and something, something, y hat. Unit vector notation simply means you state a vector in terms of its x component and its y component. So what is its x component? Negative 430, right? Negative 430 meters x hat, and the y component is 676 meters. I didn't draw that very well, did I? 676. Y hat. That is our answer in unit vector notation. We kind of went right by it, and I went right to the magnitude and direction, but you're going to need to know how to do that as well. Okay? All right. Vector C. Vector C, sorry. Part C. What is the average velocity for the walk? That's what it's asking us. Calculate the average velocity for your walk. Well, we know that average velocity is displacement over time, right? Now before we've written it in delta x over t or delta y over t. Well, our displacement is in this direction right here, that r direction. Or you can call it r or s or t or whatever you want. It's certainly not x or y. But so it's our displacement over time. And hey, we just found out what our displacement was in magnitude direction and unit vector notation. So what's our time? It's 150 seconds right there. So C is asking us, in unit vector notation, what is our total displacement? All right? This is actually going to be pretty easy. In fact, to do this, I'm going to, let's see, can I move something around? I'm going to move this down a little bit. Sorry. Move that down ever so slightly, then I'll show you why in just a second. All right? Average velocity equals delta r, our displacement over time. All right? Well, what is our displacement in unit vector notation? That is negative 430 meters x hat and 676 meters y hat. All right? So how do we take that and convert it into a velocity? This is just a displacement in the x, the displacement in the y. What do? We divide it by time. So we just divide both of those by how much time has elapsed. So that's 150 seconds and 150 seconds. Now we've turned this into a velocity. Meters per second, right? Meters per second. All we need to do is just crunch the numbers and we have our velocity in unit vector notation. Average velocity in unit vector notation is going to be, what's negative 430 divided by 150? Negative 2.87. Negative 2.87. What's that unit? Meters per second, right? It's a velocity now. Meters per second x hat. And 676 divided by 150, that's going to be 4.51. 4.51 meters per second y hat. That is our velocity expressed in unit vector notation. Okay? Now lastly, part D, you might be thinking, oh my gosh, we don't have very much space to write here. I'll do the part D. We'll do this B and then A right there. So A, B, C, and D. How do we express that in magnitude and direction? Magnitude and direction. What's the magnitude of our average velocity? Well, if you get the magnitude, you use a Pythagorean theorem, right? Square root of 2.87 squared plus 4.51 squared. That's our x squared value and our y squared value, square root of that. 2.87 squared plus 4.51 squared. Take the square root, 5.34. So average velocity equals 5.35 meters per second. At what direction? Well, we can bet it's going to be the exact same direction as the displacement, because you can't have a displacement in a direction and a velocity in a different direction, right? I bet it's going to be the exact same direction as the displacement right here, which is 57.5 degrees north of west, but let's just prove it. All right, how do we get our direction? For the direction of average velocity, we take the inverse tangent of the y over the x. That's 4.51 divided by 2.87. Inverse tangent of 4.51 divided by 2.87. I get 57.5. 57.5 degrees. We have a negative x and a positive y, so it's going to be 57.5 degrees north of west, just like the displacement. Except the only thing that makes velocity different from displacement is velocity. The displacement is divided by time. 430 meters divided by your seconds. 676 meters divided by your seconds right here. So we have our velocity in unit vector notation. We can easily take that with our Pythagorean and inverse tangent and turn that into a magnitude and direction notation. All right? So there's example 11 for you, and I hope that helps. So good luck on your test.